So again, page 223, we're gonna start with the ratio test. Okay, this is one that is useful when you have factorials, exponentials, even uglier things than what we had yesterday. Okay, and you're gonna see some ugly things today. There are three situations that can happen with the ratio test. And so essentially what we're doing, we're gonna look at, here's what's really important. I'm gonna blow this thing up a little bit here. Okay, this is the crux of the whole deal. What we're gonna be doing is you're gonna be taking the limit as n approaches infinity of the next term, the absolute value of the next term divided by the last term. Okay, so they're going to give us the term, right? They're going to give us the problem. That's going to be the a sub n. What we're going to do is find the next term after it, which is the a sub n plus 1 term, and we're going to divide them. And if, depending on what that limit is, that will tell us whether it's convergent or divergent, or we don't know. There's three cases. Okay, so the first case is up there, right? So if the limit is less than 1, okay, meaning it can be negative, it's fine, just so long as it's less than 1, then the series, the infinite series of a sub n is going to converge. Okay? If it is greater than 1 or equals infinity, and to me, infinity is greater than 1. But infinity is an idea, right? It's not a number. And so you could think of them separately. When we go through this, when we get a limit that equals infinity, I also state that it is greater than 1. There might be some, I don't know, maybe we can't say it like that, but I like to think of it that way. You know, we think of infinity as this gigantic number that we can't actually think of, but it's gigantic. Anyway, so then what's going to be our third case, do you think?
Equals.
Oh yeah, you're looking at the page. So if it equals 1, it's inconclusive, which means if it equals 1, the ratio test doesn't work. You have to find another test to figure out whether it is convergent or divergent. Okay, so those are our three cases. And it's what's going to be tricky for you is because you haven't worked with sequences a lot, is figuring out how to come up with the n plus 1 term. N plus 1 term. How is that? I don't know. I think it's the whole n plus 1. N plus first term? I don't know. Like 1. All right, let's do examples. Okay, we're just going to jump right in. Now, again, I feel like the trick for you is to come up with the next term. But here's the thing. You know, since the limit has the original term in the denominator, it's again that keep, change, flip. What I'm essentially going to be doing is multiplying the nth plus 1 term by the reciprocal of the problem. So the trick is, okay, I need to come up with the nth plus 1 term. So, let's do that real quick, right? So this part is pretty simple, right? It's just going to be n plus 1 factorial. And the bottom is just going to be 3 to the n plus 1. And that's all it's doing. Power. And so that's the nth plus 1 term. And I'm going to multiply that by the reciprocal. All this is an absolute value and a limit, and so that's where we are. Okay. That's the setup for this problem. Now, here's where some of that inexperience that you have with sequences and factorials is going to come in, right? Because what's going to happen is we're going to always be able to reduce this all down. Reduce tops with bottoms, bottoms with tops, and find ways to simplify this complex fraction, right? And I would like you to do that on your own right now. And I'd like to see how we do with that, because to me that's going to be a marker, an indicator of maybe future success and what we need to fill in. Let's start with the factorials. Those are probably easier. Okay. At this point, we've worked with this enough, so hopefully you realize that this is n plus 1 times n minus 1, meaning this is all n factorial. So that, this part and this part cancel out. So on the top, I just have n plus 1 so far out of that, right? This next part, I'm watching you get tripped up a little bit. And you're thinking about power rules and bases and what you're supposed to remember and that kind of thing, okay? Here's the kind of trick to this. There is, in reality, this means 3 to the n times 3. 3 to the 1. All right? Agreed? Because the bases are the same, we multiply, we add them. Why is that helpful, right? Well, that's helpful because then we can just see that it's just goodbye, right? And I just have a 3 on the bottom. And as you work with the ratio test more and more, you're going to see more and more problems like this with the powers, they're off by 1, which means there's going to be a base, a numerical base, either on the top or the bottom, whichever one is bigger. The factorials are going to be off by 1, so everything's going to cancel except for the sort of first term or two kind of thing. All right. Does that make sense? Does that help? All right. So where we're at with this here, okay? Now, when I find the limit, okay, the only thing that we're really concerned about at this point is n, right? Because the 1 and the 3, as n grows infinitely large, the 1 and the 3 become inconsequential. So what is the limit of this? Infinity. Okay. And like I warned you before, to me, right, infinity is greater than 1. So I just emphasize that. You don't have to. Just to be clear, you don't have to say that because in the rule, it's either greater than 1 or infinity. To me, it's just, again, in my mind, I have these 3 cases. Less than 1, greater than 1, and equal to 1. So that's it. Diverges by the ratio. Okay.
Can you say it equals infinity, or do you have to have
I think you can say it equals infinity. I'm at this place now as I investigate further and further into the FRQs that I'm like not going to write equals ever. I feel like I don't know. Because I'm not entirely sure when to write it and when not. Now, if it's a number, right? Like if it's 7, then yeah, write it. It's fine. It equals 7. But the thing with infinity is we could also say it does not exist, right? The limit does not exist. That's another way of stating it, and that would be correct. I'll investigate that a little further, but I'm getting sketched out myself writing equal signs at all anymore. So, I think it's fine. Honestly, I think it's fine to write equals infinity. The thing that I'm learning, they hate things like this. Don't write, equals that. Like they don't like that one at all. An idea divided by an idea. Like I don't know. It does equal 1. All right. Anyway, let's move on to the next one. Hey, this problem looks almost a little familiar. Kind of like number 5 from the other one. It's similar, right? But it's different. There's still a 3 to the n plus 1. There's 4 to the n, and instead of having a plus 2, it's n squared. Do you want to just try this? Give it a shot, see how you do? All right, let's do that. They really don't get hung up about the arrow. They don't care about the arrow. That's fine with them. It's so that's why I've sort of leaned that way. Like, all right, when in doubt, put an arrow. Because they don't get bent out of shape about that. But for some reason, sometimes they get bent out of shape about an equal sign. So if you want to check your setup, when you're ready, you can see the screen and check your setup before you get too far into it. Let's talk about the reducing for a second, simplifying, okay? As you get more and more comfortable with this, right? So I've got one more 3, where, on the top or the bottom? Top, so those cancel to be equal to 3. 3 on top, right? How about the 4s? Where's that gonna be? Bottom, there's more 4s on the bottom. That's kind of the way to think about it, right? Because remember what a power is, right? It's just saying, multiply this number by itself, a certain number of times. Well, 3 to the n plus 1 and 3 to the n plus 2 means the 3 to the n plus 2 gets an extra 3 multiplied by it. Same with the 4 to the n plus 1 compared to 4 to the n. Okay? Now, the one thing I want you to be careful with, because you get in this habit with these factorials and you start thinking, oh, I could just cancel it and it's n plus 1. No. There's no factorial here. You cannot cancel anything here. Be careful with that. And so if you did, you would probably lose a point on FRQ if you did that. These don't cancel at all. Okay, because think about what this is. This is really n squared plus 2n plus 1, and you can't cancel an n squared with that. So that's the part where you can get in trouble. All right, so the n squared over the quantity n plus 1 squared, there's no reduction there. But it's not necessary, right? It's basically n squared over n squared when we compare it as n approaches infinity anyway. The 1 becomes inconsequential. That just cancels out. And so yes, the limit is 3/4. Make sure to state that that is less than 1. And then we can say that it converges by ratio test. Okay. Good? Questions? Let's do another one. We're going to do 2 more. I think there are only 4 examples in the book anyway. We're doing them all. Especially because I want to talk to you about what number 4, and there's some new notation there. Okay. It's no longer 2n plus 1. It's 2n plus 1! Get it? You get it? Thank you. So it's 2 exclamation points instead of it's a double factorial.
My mom was in my room yesterday, and I was doing your homework.
Please. When you work the ratio test, this alternating sign term essentially drops out because we take the absolute value of the ratio. So this part becomes really unnecessary within the ratio test. What happens to the limit here? You're still working? Here, what do we get? With the ratio test, you don't know? All right, here's what you get. I'll show you. Okay, so n plus 1, right? N plus 1 minus 1, so that's just n. And again, we don't have to worry about this. This is the alternating sign part. So it doesn't matter. It's minus, plus, minus, because the absolute value, it goes away. Well, in reality, I have the square root over the square root, and n over n, everything just cancels. Okay, that equals 1. The limit is 1. Because this is the square root of infinity over the square root of infinity. Cancel. Infinity over infinity. Cancel. 1.
Could you also just go by the degrees?
You could, yeah. This is the top is n to the 3/2. The bottom is n to the 3/2. Sure, that works too. Anyway, it all goes to 1, which means the ratio test is useless to us here, right? Ratio test is inconclusive. Now, this is now we start talking about this idea where, I mean, the problem said determine convergence or divergence. It didn't say use the ratio test too. But we were, I'm glad you tried that, right? That's why I wanted you to try to show that, like, this isn't going to get you anywhere. When you see a problem like this, your first thought should be what? Which test should you be thinking about for this problem? Alternating. This right here gives it away right away. The next thing I want to check is the limit of this equal to 0? Because if it's not, then we're done with alternating series test. Well, is the degree bigger on the bottom than it is on the top?
Yeah.
Yeah, so the limit of this does equal 0. So we're in good shape. The next thing we got to just make sure, is it decreasing? And notice we started at 2 because we didn't want this to be 0. And so you test that, the square root of 2 over 1. square root of 3 over 2, square root of 4, which is 2 over 3. So the numbers are getting bigger on the top and bigger on the bottom, but they're getting bigger on the bottom faster than they are on the top because of that square root, okay? So it meets all the conditions. Of the alternating series test. It's alternating, it's decreasing, the limit equals 0, so this does converge by the alternating series test, okay? And so when you use the ratio test and you get this situation where it's inconclusive, and this inconclusive case is going to come up in the next couple sections after this, 9.9 and 9.10 too. But just understand that when that happens, you got to look for a different way, okay? The reality is you can use the ratio test for everything if you wanted to, just like you can always apply the nth term test. There are no conditions for the ratio test, right? There are no conditions. You can just use it. Now, if you don't, it's going to be helpful with those super complicated, expressions. But, yeah. Anyway. That's the thing that I like about the ratio test. You don't have to meet a bunch of conditions first to see if you can use it. Like continuous, decreasing, positive, increasing, there's all those conditions that have to apply first before you can use that test. The ratio test doesn't have that. All right, let's talk about the double factorial. Here's what that means. And I know they illustrate it here, but let's actually talk about it. It means only the odd or even terms. I should have said that, terms. And it's all based on what the first term is. Is it odd or is it even? That kind of thing, okay? Now, they've kind of spelled it out for us, right? And we've talked about this a little bit before, right? The 2n without adding something to it, unless it's another even number, is going to be even every time, right? So 2n is even. When I add 1 to an even number, it gives me an odd. So what it's saying is, this is the factorials of just the odd terms. n plus 1, 2n plus 1. Now instead of going to 2n, because that would be the next one down, right? But that's an even term. We skip that one, and we go to 2n minus 1. If I went to 2n minus 2, that's also an even term because I'm subtracting an even number from an even number. So in reality, this top, what they're telling us is just the odd terms. All right, and so they've expanded it because this is the first time you've seen this, I'm sure. A problem like this is perfect for the ratio test because what's going to end up happening when you have those factorials, keep, change, flip, the next term, everything is going to cancel below it, which is nice, okay? Now, keep in mind here as well, the only factorial on the bottom we have is this n factorial. This is not a factorial. This is just 2n minus 1, all right? So try setting this up. Don't go beyond setting it up. Try to set it up, and let's just see where you're at. Remember that the a sub n minus 1 is just the next term, okay? And so the term that would come before 2n plus 1 would be what?
2n plus 2.
No. It would be 2n plus 2 if we could use all of them.
2n plus 3.
2n plus 3, because it's got to be just odds. 2n plus 2 is an even number, right? 2n is even if I add an even to it. So 2n plus 3 factorial, okay, is what we have here. Then I've got 2 times the quantity n plus 1, and then I have n plus 1 factorial. And then obviously you just keep, change, flip for that one. All right, so take a look here. This is keep, change, flip. So now this is 2n plus 3, because I can't go to 2, because that's an even factorial. 3 to the n plus 1. Now, I did a little, let me write this out. Okay, so this is 2 times n plus 1 minus 1. Well, that's 2n plus 2, which gives me that. Okay, the rest of it's the same, 3 to the n plus 1, n plus 1 factorial. So if I take this, it's 2 times n plus 1 plus 1 double factorial. Right? So what gets replaced here is this n gets replaced with n plus 1. So another way to think about it, 2n plus 2 plus 1, which is 2n plus 3. So there's the intuitive way to think about what's going on with the odd factorial or the even factorials. But then, you know, we're subbing in anyway. We're subbing n plus 1 in for n to get our next term. And so that gets us here, okay? Questions about that? All right, let's talk about how we can cancel. All right, hopefully by now we're good with the 3's, right? There's going to be a 3 on the bottom. Can't cancel 2n plus 1, 2n minus 1. Those are not factorials. So those are both going to be there. But it's fine because they're going to cancel out anyway, right? Because the limit of this, as it approaches infinity, and this is infinity over infinity. So it doesn't matter. Okay, the n factorial, the n plus 1 factorial, that leaves me with an n plus 1 on the bottom. And this one leaves me with a 2n plus 3 on the top. So here's where we're at. 2n plus 3 on the top. The 2n minus 1 is still there. The n factorial and the n plus 1 factorial, so that's where that comes from. Let me highlight all that. I think that'll be helpful to see where they all come from. So this comes from here. All right. The 3 comes from here. And then the 2n plus 3 comes from there. Okay, and the 2n minus 1 is still there. We didn't do anything with it. The 2n plus 1 is still there. We didn't do anything with that. Okay, so that's how that reduction, that simplifying comes in. And then we'll take the limit and be done. Let me go here. If you want to think about it this way, this really is 2n plus 3 times 2n plus 1 times 2n minus 1 times 2n minus 3. Well, all of this is 2 plus 1 double factorial. So that's why, again, everything all cancels all the way down except for the first term. The same way that we did right here. So that's why I say the ratio test is really nice for factorials, because those factorials generally mostly cancel out. Okay. All right, let's finish this limit. All right, now we're looking at leading terms. So I got 2n and 2n, that's 4n squared. Then I got a 3 times a 2n times an n. That is 6n squared. So I have 4n squared over 6n squared. That's really what we have now.
Can you just write that?
Yeah.
Like even without all, because it's
Yeah.
technically it's not the...
Yeah.
Okay.
Because that's what we're finding. Yes, they are not equivalent. And I didn't, so here to your point. I wrote it on a separate line. I did not write an equal sign that said this is equal to this, because if I did, I'd have a linkage error, because they are not equal to each other. Their limits are going to be equal, right? But this is not equal to this. And so then obviously the n squareds cancel. My limit is 2/3, which is less than 1, so it converges. But that's a good point. By the ratio test. All right. All right, I still got a couple minutes. So there's 2 more slides here. And the 2 other slides are about putting it all together, okay? And I'm not going to go through and explain it very much, but they're in your book. Both in there. And we're going to just spend more time talking about that as we approach that, because we're just going to be practicing. We're just going to say, find convergence or divergence, and it's going to be up to you to figure out which test. And the thing is as we work on this more and more and more, you're going to start recognizing the form and be like, oh, this, like that alternating series test. Like, this makes sense to use alternating series test here. Oh, there's crappy factorials. We probably ought to use the ratio test here. Oh, it looks like really close to a p-series. Maybe we should use that kind of thing, okay? Anyway, and so here's, I understand, I need to get through this though. How to handle these mixed problems. This is important, okay? It's talking about, do the nth term test first, always. It's super easy. Bam, knock it out, okay? Is it special? A p-series, geometric, alternating? Then consider those tests, all right? Is it easily integratable? If that's a word. Are there factorials or exponents? Okay, can you compare it to something else that's simpler that basically is close to the same thing? Right? Those are the kinds of questions we need to start asking ourselves. And because there we go. We have them all. There is the list of all the tests. And as we move forward toward our test, as we move forward toward the exam, it's going to be trying to figure out, when do I use what? Because now we have all the tests that there are. Okay? So let me go back to